Hello everyone. It's really nice to be here in the city that almost has the same name as I have. So Riika in Riga. Second time that I have ever been in Riga. I will talk about three things if I have time, I hope to. So I modified the title of the presentation a little bit on the history and future of ALD, about VPHA, we'll soon know what that is about, conformality analysis and mechanisms. And if I start running over time, please warn me like 5 minutes before time, then I will just cut it. So VPHA stands for Virtual Project on the History of ALD, and we have been finding out about the facts behind the history of ALD, as I a little bit pointed out earlier today. And the first part is fully based on a talk that I gave last fall. There was a Baltic ALD meeting in St. Petersburg. This was quite historical because there has never been a so-called Baltic ALD meeting in St. Petersburg. This is a conference series that started between Estonia and Finland, and it has expanded to other countries, and this was the first year ever that it has been in Russia. And you can find that presentation slides in the internet fully, and also in YouTube you can find a record of it. I will should be showing some of the slides here. Then I will talk about something real which we are doing at the moment at VTT. We are developing chips for analysis of thin film conformality, especially aimed for ALD, but they can be applied for other things also. This work is ongoing, and there is a website actually, pillarhole.com, where we are updating the most recent big things. It's probably going to be renewed within a few weeks. And this year I will be talking about these things in many conferences. In Linköping, who comes there will hear more. In ALD 2017 you will hear more. And also if you come to EuropaCat or ABS conference, this is something that we are really now working with. And then I will point to some very basic open questions regarding understanding the surface reaction mechanisms in ALD, if I have time. And that is also fully based on an earlier conference presentation. So last summer at the large international ALD conference called ALD 2016, I had a presentation, and I'm just referring back to some of that material, and that presentation you can fully find in SlideShare. I would like to dedicate this presentation to late Mr. Sven Lindfors, or Svenka, as we learned to know him. He is a core pioneer, or was a core pioneer of building ALD reactors. He was a very close collaborator of the Finnish inventor of ALD, Tuomo Suntola, from 1975. So just a year after Suntola started working with ALD, he paired up with Sven Lindfors, and they have worked until the end together. He is also the founder of Picosan, which many of you nowadays might know as a very good equipment manufacturer. Sven was also the, let's say, cover or heading boy of our exhibition, 40 years of ALD in Finland, which we organized in 2014. You can also find those exhibition materials in the internet. These presentation slides contain links, and you can just look for Fin ALD 40. It points you further. And then a little bit about me before I start speaking. I don't think that I know anybody of you earlier, so it's nice to see so many, get to know so many unknown faces. I have been working with ALD since 1998. That's when I made my master's thesis to microchemistry, the company in Finland, which was then bought by ASM, and which has actually been in the very core of bringing ALD to the microelectronics industry. I made my master's thesis there together with Suvi Haukka as the advisor, and that's where I also met Tuomo Suntola for the first time. Then I continued for a doctorate. This was related to catalysis research at Fortum Oil and Gas in Finland. and I was a postdoc at IMEC in Belgium, and from 2004 on I've worked at VTT, Technical Research Center of Finland, taking ALD into use in MEMS fabrication, microelectromechanical systems. And since February this year, I have been now part-time, later full-time, a professor at Aalto University, and the area there is catalysis science and technology, so in a way I'm going back to what I made my thesis about a long time ago. You can find me in Twitter, LinkedIn, and so on. And something that you might have encountered, maybe not, are these reviews, ALD reviews, which I have written. Journal of Applied Physics, 2005, that was for many years world's most cited review on ALD. Nowadays no longer, because this position has been taken by the Stephen George review. And then together with the University of Helsinki professors and Ville Mikkulainen, we kind of updated this, and then there is one further history review in Journal of Vacuum Science and Technology A. So these are maybe the major outcomes of my ALD work. And also we saw the periodic table of ALD. That's also something that I have first published in the 2005 review. It was updated for the 2013 review, and now it would be very nice to update it again, but it's a huge work and I don't yet know how to get it done. First time I did it myself, second time it was Ville Mikkulainen, and now I'm somehow thinking of this ALD community is building so much, and I'm very much for open science, open collaboration, and I would somehow like to make this an international collaboration. I don't know yet how. And I'm also the coordinator of the virtual project on the history of ALD, which we started in 2013, and I have had much support from other people who kind of co-founded it together with me, and more than 70 people have joined by this time. So, getting to the first real part, the history presentation. I gave this in the fall. This is a photo taken of the talk by Kaupo Kukli from Estonia, who will be here tomorrow. There were about 40 persons in St. Petersburg then, and now we jump to that. So this was a joint presentation, invited talk by me, and these people have been in the core organizational group of the history project. Altogether we are now more than 70 people, but this was an organizational talk rather than an talk really scientifically. We have seen today already twice basic schemes about ALD. I would just like to go through the very, very core of ALD, maybe again, or maybe for the first time. I don't think that I heard these words really. So what is ALD? It's a chemical gas-based technique for growing thin films. It's based on repeated saturating irreversible chemisorption reactions of gaseous compounds that are compatible for the growth. So you grow a film by repeating the same reactions again and again. Here you have seen, here is one representation of an ALD cycle. But it's the basic requirements for, let's say, ideal ALD. They are rather simple. You have to have a reaction that is saturating. So it means, can I point with something? I will just point with the mouse maybe. Saturating, it means that the reaction stops by itself. And irreversible means that when you remove the gaseous compound from the gas phase, you still have the amount absorbed there, which you did. So saturating and irreversible. And when you have these types of reactions, then you can basically grow a layer as thick as you want. This example is from Estonia. Kaupo Kukli might be one of the authors. It's by Professor Aarek et al. From a long time ago, and I have asked for permission to use and color that one. So many classes of materials have been made by ALD, and this is the same data that was shown in a presentation earlier today by somebody. It's from this second big review of me. A point that I would like to make here is that it's not a table that shows what is possible, it is a table that shows what has been tried. So don't think that this is a fundamental limitation of ALD. Somebody noted already gold has been grown. Yes, this was the time at the end of 2010, and much has been made after that, and much will be made in the future. So this is just what the scientific world has tried, an overview of that. Yes, ALD has been discovered and developed independently twice. I don't know if this became clear yet. Maybe not. We heard of Alekskovsky's work and of Suntola's work, and there were probably quite many who heard about Alekskovsky for the first time today. Can you raise your hand if you never heard about him earlier? A few hands rise. Who heard about atomic layer epitaxy? About a bit more hands, yes. So certainly, atomic layer epitaxy and Suntola's invention in Finland is more known in the world. It's the basic way that all reviews described ALD. But it's also a fact that ALD has been discovered by the Russian authors Alekskovsky and Kaltsov. They didn't call it ALD, also Suntola didn't call it ALD, they called it molecular layering. And yeah, it has remained poorly known and cited. What are the reasons for that? There are some good ones and some bad ones, but a fact is that these both should be known, and we have worked a lot to dig up the real facts about these in the virtual project on the history of ALD, because we want to know. Scientists want to know, right? We want to know the facts, and then we move on. And now I will just show a few important steps in the history project. So before going there, citing two major reviews on ALD from Knees Niinistö from 2007. So they only mentioned the Suntola work. George, the most cited review on ALD of the world at the moment, he also just says ALD dates back to the 1970s in Finland, point, nothing else. And so I graduated in 2002 with a doctorate from the University of Helsinki. This is from my thesis, and you see, I mentioned there molecular layering, atomic layer epitaxy. So I knew of the name. I didn't know how old the technique is, but I had encountered the name. And then there is also from Vitala Leskela review, it's a book chapter actually, 2002. They also mentioned molecular layering as an alternative name to the ALD method. And there they say it dates back to old Russian literature. They didn't give any references, but they said this. It dates back to old Russian literature. So this is already something that it grabbed my attention. And then in 2002, Professors Malygin and Smirnov from St. Petersburg published, actually it's a comment on another paper called Early Work on Atomic Layer Deposition Cited. I was at IMEC when I got this work. Somebody brought a copy to my table, and combining these two things dates back to old Russian literature, and then this work where they actually gave some of the citations, and there was an email address of Malygin, Professor Malygin. That's where everything started, because I contacted him and asked to get some original references. So I wrote them up. In the first big review of mine, there is a separate table of some Soviet-Russian ALD investigations. It says some because I got the references, I read them, I found more, and I understood that this never stops. I had something like 150 references, some of them in Russian, some of them in English, and I felt like it's far too large a task for me as a postdoc alone to go through this. I decided I have found enough evidence to know that A, it is ALD, and B, it is older than the Finnish works. So I wrote it up and published, and I thought that that's my part of the history of ALD. So that's in 2005. Yeah, the less commonly acknowledged origin of ALD dates back to the Soviet Union in the 1960s in the group of Professor Alekskovsky. So this information would be from 52 from Alekskovsky's own thesis. I believe that there's no basis for that. We have gone through that in the history project, and I have a copy of the book, and you can have a copy of it too, and look for yourself and form your opinion. But there's no repeated cycles yet, so it's a basic citation. It's part of the evolution in Russia, but it's not really part of ALD yet. So the history project really started from a question made by me in LinkedIn, because somebody told that in early 1960s there would be ALD papers. So I asked, what are these actually? Because I didn't know any. Mine were from mid or after. And that's how it started. And so we started discussing, and we came up with this project with the goals to find out how was the concept developed, what were the first ALD experiments, when, where, and by whom were they made, why were they made. We are curious scientists. And how to do this big task, we decided we need to have a full list of early ALD publications. We need to read them through by ourselves, not rely on what somebody says. I know there are so many rumors going on of ALD's early days, and more than half of them are not correct. We have to read them and form our own words about that, and we should share these. And everything should be done in an atmosphere of openness, respect, and trust. This has been really important because we come from different backgrounds, and there has been maybe not conflicts about this, but there have been people who are being upset by not being acknowledged properly. So it has been really important to do this in an atmosphere of respect and openness and trust. And we have a file called ALD History Evolving File. It's a Google document. You can view it in real time. In the fall, it was already 300 pages long. It has the citations and people's comments on that. So the goal is that each paper would be read at least by 3 people. We didn't get quite to there yet. And yeah, the project was opened, and it was opened also. People were invited to participate in this ALD 2013 conference. I got an announcement there made by the conference chair. And just there I learned that people were writing a review about the history of ALD. These about 10 very, very highly knowledgeable people led by Professor Gregory Parsons, who also wanted to know about the history of ALD. And this was a paper about to get published at that time. And I was thinking, ooh, we just came up with this history project. Is it no longer needed? Did they find it out already? And well, they do acknowledge their molecular layering, but what they say is that a planar film was not produced or evaluated, and this is also not true. So they didn't really do the work that we still need to do the history work. And many of these people have high respect also for the history work, and Leskela actually has participated in. So there have been meetings and visits and coincidence. So I visited St. Petersburg for the first time in 2013, and that was an important kick to the history project. Here is Professor Malingin, and that's Professor Drost. They work in different laboratories. Both have been founded, I think, in the 60s or in the 70s. And in his Malingin's lab, they have been working with ALD all through since 60s. That is maybe the oldest living person who has the longest experience in ALD. I wrote an essay about the Finnish atomic layer epitaxy. This is published in Chemical Vapor Deposition, and also there was this exhibition. This is just a summary of that would be from 1980. This is actually the first public demonstration of ALD. In 1980, Suntola presented a demo of an electroluminescent display. That was the first public one, and this is Sven Lindfors with his reactor, and Suntola in getting the SEMI award. By the way, at the top there is kind of a timeline going. The years are not indicated in numbers, but they are in the correct distance. So about a year later, there was an ALD Russia conference organized, first time ever an ALD conference in Russia in English. And this is where the different countries met. This is a very symbolic picture. That's Malingin, that's Gregory Parsons, that's me. that's Steve and George. They actually came to Moscow in 2015. That was a very, very important event also. And they have been writing an essay about molecular layering on request of others. You can also find this. And the photos tell so much. Here are some of the early reactors. And also, these guys have also met. There's Suntola, Drost, Leskela, Niinistö, George in the same picture. And last summer, in the big ALD conference, for the first time ever, a person originating from the molecular layering side gave an invited talk. This was actually a plenary talk at the big ALD conference. And last thing, a joint manuscript has been written from the history project, recommended reading list of early publications on atomic layer deposition. There's a list of 22 papers which came out as the most important ones through voting. And this one has been published in the meantime. Now I'm stepping back to my current presentation. So it's in Journal of Vacuum Science and Technology A, and it has 62 co-authors. And it was featured and most read for several months. Now it's number 2. And we are not very actively working now in the history project, but it is still open, and I here also sense that there would be a need for a good history review on ALD. Maybe this will once come. If you are interested in contributing to the history project as a volunteer, you are most welcome to join, and we will provide you with these copies of the early papers that you want to look at, and we very much appreciate if you can give back comments on how you see the contents. So info@vphald.com, that's the address to contact. Moving to the second part, ALD conformality testing. So here are the basic references. I will jump further. Conformality. Would everybody right away know what we are talking about when we are talking about conformality? Well, it would be the ability of a film to cover a complex 3D surface with the same film everywhere, with the same quality, same thickness and same qualities everywhere. And ALD is renowned for its conformality. That's, if you need a conformal film, there are some cases that you cannot use anything else than ALD. So this is a demonstration or idea of ALD catalysts by Suntola long ago. From MEM structures, protected coatings for silver. In microelectronics, of course, there are more and more applications coming where complex 3D structures need to be covered with a very, very uniform thin film. Here are some structures that have been used to characterize conformality over the years. That would be porous silicon. Here are anodic alumina pores which have been cut from different places. Then very typically trenches or holes are etched into silicon, and earlier they were not so very demanding. This is something like 5:1, and here is already 40:1. And then also we are working with lateral high aspect ratio test structures, and also in Belgium there is a group working with these bigger ones, macroscopic self-built screwed things, but we are working with microscopic structures. You there, are you also from this group? Yes, I thought so. Professor de Tavernier's group, yes. So VPT's approach at the moment are all silicon, microscopic, lateral high aspect ratio test structures. This is the prototype 3 that we have at the moment. I have one example here. Would you be interested in looking at it? Please don't drop it. So these are 15 times 20 millimeter at the moment. I'm trying to make them very easy for people to use. That's why they are at the moment a little bit big. So they have membranes which have one side open, and they look like this. Sometimes they are mirrored. Well, the biggest one is not mirrored, it's open only on one side. So it's a membrane that is supported by pillars. And there is a gap of very controlled height underneath. It's typically 500 nanometers. I see that I should write it here. And this is all the information. 500 nanometers, and at the moment we are making tests with 100 and 2000 nanometers too. So 500 nanometers, making it a microscopic structure so that the flows inside are corresponding to the ones that you typically have in microelectronic industry. So you have molecular flow at typical ALD conditions. There are 3 publications at the moment. The first one, 2015, where we introduced the concept, and then 2 more to come. But there is nothing yet of this third generation prototypes that we work with at the moment. And here is a picture of a barrage. So really this is a good analogy for what we have. It's like a huge area where you have pillars that make the roof stay in place, and the good thing here is that you can also take the roof away. You can analyze these in really many ways. This is a microscopy image, and here is our opening to the membrane, and this is just plain silicon. It's all silicon, by the way, everywhere. And here under, the film goes in, and then you can, for example, just by regular microscopy, visible light microscopy, in some cases see how deep it goes. You can see the pillars and you know their distances, so you can actually very quickly say that it went 100 micrometers or something else. Of course, you can also cut them in half and investigate with electron microscopy, just like the vertical ones that people normally are used to looking at. Where things get really interesting is if you remove the roof and you expose the film. Like here we have removed just with regular tape, adhesive tape, taken away the membrane, and then you expose the film directly on silicon. This one you can measure by many means, I think. We have done it by reflectometry, and here are just repeated line scans. This is for the basic TMA for the process. You see, you always get the same result, so the repeatability is very good. And here we see basically the shape that we would expect for a good ALD process, that you have just a constant plateau, after which you have a fast decline of the thickness. And yeah, the interesting thing is here, the previous figure, it had like 200 points. There has never been access to such information earlier, because when you have these vertical structures, you measure point by point. It's very, very tedious to do something like wafer mapping. Here we can use these automatic mapping methods and get very, very detailed information with which you can, of course, if you know how far the film goes, you can optimize your purge times, you can understand the reaction mechanism also if you look at this, because TMA water has a flat plateau here, but not all films will actually be flat. So you get to these, is it irreversible, is it saturating, and what are the kinetic parameters of the reaction? So this how steep is the slope will be related to the fundamental kinetics. I think that this will open up a lot of new avenues for research. And we are also doing some modeling ourselves. I have a colleague, Markku Ylilammi, who is actually, he made his thesis on ALD in '79, so pretty experienced in ALD, but he has actually been doing other things. He's an expert on modeling, and he grabbed the chance of doing modeling for ALD, and this is one of our graphs for TMA water process, and he has extracted a sticking coefficient of 0.0108 and an equilibrium constant for the reaction, and also calculating the TMA partial pressure at the inlet. This is not, I don't present this as something final truth, but it's rather ongoing work, because yeah, I hope that we get to publish these ones one day, but it's possible. But these are excellent for testing models. You build a model, you need experimental data to compare it to. With these chips, you can generate that. So imagine what all can be done with these chips. How uniform are the films actually inside the 3D structure? Does the composition stay the same? Does the morphology stay the same? How about the electrical properties? What's the highest aspect ratio one can quote? At the moment, the record is at 3,000 to 1 with these pillar hole test structures. Who can go and which process can go deeper? What methods can be used for non-destructive analysis? What methods can be used for these line scans and extracting kinetic information? How small does the spot size have to be to get reliable information on the slope? And how will our understanding of ALD evolve through exposing this new parameter space? I think that this can lead to rich research if we are able to do this properly. So I have a project going on where we can have external people doing proof of concept studies. So we are willing to give people, you if you want, these chips for testing. Now it is at the stage where we are doing this for free with the purpose of joint publications. Later, I hope that this will be available for purchase. They are not that yet, but well, we are willing to collaborate with people who want to do and to measure. I think that this is an excellent place for doing good science in an easy way, actually. Because it's, you take the chip, you code it, you analyze, and you already produce something that is nowhere in the literature at the moment. Of course, in a few years it will get more demanding. So if you are interested, please contact us. And I have actually the chip that goes around. I can show you with my carry with me demo. There's a mobile microscope that I can put to this telephone, and then we can actually look at the film. The one has 100 nanometers of aluminum oxide, but this is basically what you will see if you look at it like that. So during the next break, I can show the demo if somebody wants. I think I have a few minutes more. Yes, okay. So now I proceed to the third part then, to reaction mechanisms. And this is a talk from a talk that I gave last summer. Comparison of interpretations on the surface chemistry of the trimetal aluminium water process. This process was first published in 1989 by American researchers, to the great surprise of my Finnish colleagues who didn't expect anything like this. And they were actually surprised that the Americans didn't patent it, so it's open, it has been open for everybody all the time. So they were able to deposit aluminum oxide. We know that it's a really easy process. And they said, the authors Higashi and Fleming, the overall mechanism of deposition is extremely easy to understand. Surface OH groups react with TMA. This leaves a methylated aluminum atom behind, free to react with water during the next vapor pulse. We saw this already today, right, in this Cambridge Nanotech video and other schemes. A detailed understanding of the growth process, however, requires that one explain the anomalously low growth rate, 1.1 ångström, approximately half a monolayer of aluminum oxide. This result is not understood at the present time. I don't think that it became understood in the schemes either that we saw. They showed a monolayer growth per time, but it's not a monolayer. It's about half or 30% of a monolayer. By this time, I think that I can say that this process has evolved into the model system of ALD. Whether it is a good model system can be discussed, and I know that not everybody likes it, but it's kind of a fact that everybody refers back to it. It's like a benchmark. And why did it evolve to that? Well, it's an easy process. It has been studied a lot, and it has been reviewed separately. That was my first review, 2005. It was about this process, the surface chemistry of ALD in general, and the case study of this process. So these are the two most cited ALD reviews at this time. So George also attributed it to my review that it has developed as a model system, and many others have referred to that later. And yeah, these have been highly cited indeed. So if it's the model system, let us treat it with the critical eye that a model system deserves, right? Because anything that we understand from this, we can maybe apply to other systems. Some fundamental questions related to surface chemistry of any ALD process, which I have in my mind. How does the GPC, growth per cycle, sorry for not writing this, okay, it is written there. How does the growth per cycle vary with temperature? What is the ALD window of a given process? So at which temperature range can you use it? TMA water you can use at room temperature up to 300. Some have a very, very narrow window of some tens of degrees or so. And to me, this has always been puzzling, as to Higashi and Fleming. What defines the growth per cycle? Why do we get this number that we get? It should be, and often is, reactor independent. It's defined by nature. What is it? What's the limiting factor that gives us this exact number? What's the thing that causes saturation to take place at that level? And which surface reaction mechanisms take place and how fast they are, if you go to kinetics. And this is my postulation that I made last summer. Different works explain the variation in growth per cycle in significantly different ways. And there are 3 reviews, actually, where I refer to mine, where I went through what was studied of this process earlier, George's review, and then there is a review by Knapas and Ritala, where they go through the in situ studies, and they also, of course, refer to this. And here I will not have time to go through all of this, but you can, if you are interested, my presentation is in SlideShare, you can view it fully. But this is what I did actually in my doctoral studies. I was investigating this exact reaction on porous oxides, high surface area, alumina and silica. And the great thing in those is that you can actually control and measure the OH group concentration. You have such a high surface area that you can use totally different analysis techniques as you can for silicon wafers. So we prepared aluminium oxide heated at 560 degrees centigrade that had 3.4 OH groups per square nanometer measured by hydrogen NMR. And this, you react with TMA at different temperatures. You measure, well, this is alumina. The alumina is calculated, metal group content is measured, alumina is calculated from OH metal. But here you look at the metal group concentration. You have a flat line. So TMA reaction temperature has no influence. Then, varying the substrate heat treatment, giving a different OH group content, as seen with these unfilled symbols, and doing the reaction at the same temperature. Now separating the OH group contents influence from the reaction temperature, which influence we saw it here, but anyway they can be separate. You see, they are changing in the same direction, but the slopes are different. So there is no one-to-one correlation. There is a correlation, but it's not a one-to-one correlation. But we know here all of them, OH, aluminium, metal group, so you can actually plot this and well, yeah, that's what I already said, it's the same. You can, of course, plot this amount of aluminium adsorbed, which is directly proportional to the growth per cycle, as function of OH group concentration. You get a nice straight line. If you think of the mass balance, you have a tri-methyl aluminium molecule. It comes to a surface with its 3 methyl groups. It sees an OH, a methyl group goes and reacts with the OH and leaves. And the rest goes there with one less methyl group. So the amount of methyl groups is exactly 3 times the amount of aluminium groups adsorbed minus the amount of OH groups reacted. This one you can rewrite. You get aluminium content, that is 1/3 of the amount of OH groups that reacted, plus 1/3 of the amount of metal groups there. So you can compare that one with an experiment and you see that they are the same. So this experimental result is in line with complete reaction with OH groups, additional dissociation or association, because we actually have here a moment where we have more aluminium than we have OH groups. So it's not only OH groups. And until reaction stops by steric hindrance, because we always saw the same amount of methyl groups. When you have about 5 to 6 methyl groups per square nanometer, that's when there is no space for more. At least as I see it. Now I skip, as planned, over the other explanations, but this is the conclusion slide from last summer. So explaining the less than monolayer growth per cycle and the temperature trend, I claim at least that I have a quantitative explanation for that. In the George review there is a qualitative explanation. Knapas and Riika didn't try to give any explanation for this. Description of the growth per cycle change with temperature. From the data in the background, we see that it decreases with decreasing OH group concentration while methyl group concentration is constant. George's background data says actually that the methyl group concentration also decreases. And Knapas and Riika say that, well, N over Z, they talk about that it's about constant. So, to make it really visual, I think that there are fundamentally different interpretations. One review says methyl group concentration is about constant, one says that it decreases, one says that it increases. I think that there is something to look into further, where you can make new experiments, provide new data, support for some of these interpretations. Before I raised this last summer, I think that nobody had noticed. Because I made the review in 2005, and I have been thinking of this, it has disturbed me how I see that things go. I have felt that there is a disagreement in a way. And yeah, I think that because this is a model system, there should be looked into this. And new research activity is most welcome. And if somebody shows me that it's something else than I showed, then I'll be fully happy. If there's the true evidence, and we can all learn about that. And just jumping to the conclusion of this talk, I hope that you have understood that the view of history of ALD is changing right now. There is no balanced full review of ALD, which would tell about all history. If you are interested, I recommend reading the ALE atomic layer epitaxy essay and the molecular layering essay, plus the review article which we wrote and was published early this year, which gives the recommended reading list of ALD publications. Pillar hole conformality test structures, if you are interested, please contact. And if you like fundamental studies, I'm very much supporting them. Something that I have in the list of things to do this summer is to propose ALD and Tuomo Suntola for the Millennium Technology Prize 2018. The deadline is in the end of July. I think that ALD perfectly matches the requirements. Tuomo Suntola is the sole living inventor of ALD, so it's him, really. So I will propose him. If you think that ALD would deserve this, and if you are able to support this, you are most welcome to write a support letter. There's an example of what I wish. So I will make a long, full proposal, but if people can send in 1-page or 2-page letters, I would like to have them from all over the world to see whether ALD could really have this. So, thank you.
Thank you very much. Maybe time for one question.
Yeah, quick one. Sorry, okay.
In your title was words on the history and future. So how do you see the future of atomic layer deposition?
I feel that it's just growing all the time, and it's expanding to new
areas.
Yes, so I started in '98. I was done with my doctorate in 2002, and I felt like it's an S-curve that is going up. I didn't want to give up, that's why I stayed in the field. we are still in this S-curve. It has continued from then on. It's going to level off, but I never felt it yet. I don't know when it's going to come. So I see it as a very, very bright one.
Thank you.